Right, so there are 2 lessons left, and the good news is we're not affected by any strikes tomorrow since you don't have classes with me tomorrow. This is good. What? Yeah, here's hoping. But there's no Monday anyway. Tuesday? Alright, you're asking a lot for it to last that long. Asking a lot.
No budget for 5 days.
Yeah, too much. Anyway, we have Photoelectric Effect today, and then we have Quantum Mechanics next week. And as a special bonus, I'll do one topic in the 1-hour class next week that's not on the syllabus, but I think you might find it interesting. It is what is inside a proton, a neutron, and an electron. That's right, there's stuff inside them. Yeah. Which I don't know if you knew that. Did you know that?
You told us.
Yeah.
You said it before we were talking about it.
Yeah. So yeah, it turns out there's stuff inside of protons, neutrons, and electrons. It is not on the course, although they have mentioned it in past exams, but not as a question, as just like a background to a question. You know, the question will say something, a blank is inside of a proton and it's traveling with this speed, blah blah blah. How long until it, I don't know, travels? You know, it's a normal mechanics question, but they made it for something inside a proton. So it's good to do it because it gives you vocabulary, but don't feel like you need to remember anything from it for the exam, except for the vocabulary. The names of the things inside of a proton, a neutron, and electron. Just so if you see the word lepton, you won't go, what the heck? I've never heard that word before.
When
okay.
Was this discovered?
Literally just a few decades ago, like maybe 20, 30 years ago. It will be the newest part. It's, you know, that stuff they do, Large Hadron Collider, it's all about the stuff inside of atoms, inside of protons, neutrons, and electrons. So this is really recent stuff. Okay. You just moved, Hal. Leave Joshua alone. He gets enough bullying from his maths and physics teacher. Come up, please.
You can come up in front.
Yeah. Guys, please. You're making your teacher feel tired and sick. Right. I have to type because my writing pad's not working at the moment. Okay, so what we're looking at now is photoelectric emission. Can you see? I'll make this font larger. We shall go, guys, photoelectric emission. Now, this is something we made from in chemistry, and it was discovered by Einstein, and in fact this is what Einstein won the Nobel Prize for. But when you have a metallic surface, a conductor, and if you shine light on it at the right frequency, you can free some of the electrons from the metal conductor.
So that's what we're going for, heated electrons.
No, it doesn't have to be heated, but heating it just helps to free the electrons. Because you're giving it extra energy. Anyway, this is the photoelectric effect. It is the release of electrons from a metal surface when light of the right frequency is shone on the metal surface. Have you done? Is this a chemistry thing you've done or not? No, it's not. Okay, would you do some kind of fluorescence or something in chemistry? No? Okay. So we'll write the definition down. The photoelectric effect is the emission of electrons from the surface of a metal when electromagnetic radiation of a suitable frequency falls on it. Yeah, it is a bit like your the electrons are being evaporated from the surface. Now, in fact, this is like something you've done in chemistry. It's like ionization. So you give the electrons enough energy, and you free them, basically. But what's really interesting here is that this would seem to say that the energy of the light depends only on its frequency. Now that might seem really, really strange. So you would think if you have a metal surface and you want to give the electrons energy, you could shine some light on it. If the electrons don't move, you think, oh, not enough energy. I'll shine more light on it. But you're like, nothing happens with the electrons. They don't become free. But if you change the frequency of the light, then you start getting the electrons to be free. So this is important because it tells us that the energy of light only depends on the frequency of the light.
But changing the frequency doesn't increase the speed?
No. Does not.
How do you mean the electrons?
Well, what you could do is you could set it up in something called a photocell. So you know when you have moving electrons, that's a current. So you just could connect it around like a voltmeter or something. I'll show you that, yeah. But my writing pad's not working, so I have to draw this with my mouse, so it will look bad. I'm telling you this now before I draw it. I have to reboot it, this is the problem, which I'll do in a bit. Light comes in. It's light. Now, this would be inside of some kind of glass box. So, in red is a glass box around the metal, and it's a vacuum, so that the electrons, when they leave, they don't hit into air molecules. So I'll put this in a glass box in red. And then what I'll do is on the top of the glass box, I'll put some strips of metal as well. Just little strips, not many. And then what I'll do is I'll connect to the strips and then connect to the metal plate a voltmeter, left voltmeter. Not quite, because the capacitor is two metal sheets. This is just one metal sheet and some copper or whatever strips of metal. So it wouldn't be a capacitor actually. Again, I'm sorry, the writing pad's not working, so you'll just have to live with this. So what happens is the light comes in, hits the metal, the electrons are freed, they move off the plate, there's no air so they don't hit into anything. Some of the electrons will hit the copper strips, and I suppose if they don't, they'll just hit the glass and maybe bounce back down, but some of them will hit the strip. So actually what you can have is you can have the electrons moving in a circuit. They go up, touch the copper, go around, and then back to the metal plate at the bottom. So then, Daniel, you know that this is working because you'll get a voltmeter reading, a voltage. In fact, this is a solar panel, a type of solar panel. Because you can just replace the voltmeter with like a radio or whatever, and instead of measuring the voltage, you could use the voltage to power something. So, if you want to make a solar panel, all you need is a clean sheet of metal in a glass box that's a vacuum, and then some strips of metal on top, and then just connect whatever you want to it. Now, the only thing is there'll be a very, very small voltage, so you could power maybe like maybe a radio, maybe a alarm clock, more likely. But still, it's there. You can measure the voltage. This is called a photocell. Photocell. Yeah, it is my first grade, isn't it? My first photocell. What's wrong? Photocell. The blue is a glass box. Oh, sorry, the blue is metal. The blue is metal, the red is glass, the green is light, and the black is a voltmeter. What? I'll do it when I are in between topics. Okay. Can I go on to the next definition? So I just said if the frequency is correct, you'll free the electrons. So there is a minimum frequency, and if the frequency is more than this, it will free the electrons. So this frequency has a name. I wonder if anyone knows what it's called, if they've done this before. The something frequency, yes. The threshold frequency, yeah. So the threshold frequency is the minimum frequency necessary. Okay. Now, here comes, I suppose you might say, the problem. If light is a wave, then when you shine light on a metal surface long enough, then the electrons should get enough energy to escape. So the way I suppose you could think about this, if light is a wave, so we think light is a wave. So if it is a wave, then when you shine it on a metal surface to give the electrons energy, if the electrons are not free, then if you just keep shining the light on it and give the electrons more and more energy, then eventually they should get enough energy to be free. So the example I want you to imagine, to compare it to, okay? Imagine, I don't know, you have like a wall at the edge of an ocean. Like on a coast, you have a wall, okay? The wall is a strong wall, but not very, very strong. So if the wave hits it, a big wave hits it, and the wall doesn't break, you think, okay, well, I just wait long enough and the wave keeps hitting it, eventually the wall will get enough energy to break. So what I'm saying is the electrons are trapped on the metal. We are trying to give them energy. If I give it energy and it's not enough energy to free the electrons, that energy hasn't disappeared, it's gone into the metal. So if I just keep shining the light on it, or if I shine more light on it, then after enough time, the electron should be freed. You know, it's a bit like if you heat the metal plate, and if you heat it long enough, the electrons will be freed as it gets hotter and hotter. So likewise, if you shine light on the metal, and if you shine it long enough, you would think the electrons would then be freed. That's what I'm saying here. Okay? So if light is a wave, then when you shine light on a metal surface long enough, then the electrons should get enough energy to escape. If you just wait long enough. On any frequency, yeah. That's what should happen, and it does not happen. Yeah.
So, according to the statement, anyway, just as long as you wait long enough, should free an electron.
That's what you'd expect. But it turns out this does not happen, and this presents a problem. So this is not the case, though. What?
But why is that not the case?
Well, funny enough, that's what I'm going to do next. I thought my style should be clear now, so I do something, I'm like, oh, it's not like this, and then I explain why. Yes? So here comes the explanation. Just so you know, I think here, the type of number you're talking about here is 900 seconds. I think this maybe is for visible light, for most metal surfaces. You think it should take 900 seconds, but it turns out it doesn't. It only takes 10 to the minus 9 seconds. So not only is it not true, when you do free the electrons, they free a lot quicker than you would think.
So that's why it's not the case.
Well, yeah, number one, if this was true, hang on.
So it's collecting the second.
Oh, yes.
Just a tiny amount.
Sorry, just to be clear, by long enough I mean 900 seconds usually. But this is not the case. This is the number for visible light. Where the number comes from, it's not important because it's not 900 anyways. This is just what people thought.
You just example is long enough.
Yes. When I say long enough, do I mean hours, years, or, I mean like minutes? Okay. When electrons are freed, it takes only 10 to the power of minus 9 seconds. So not only is it not what we expect, it's way different than we expect. As you said, much less than a second to actually free them.
Right, at any frequency?
No, at the threshold frequency. So I'll just put that in as well, Joshua. And this is only at a certain frequency. Okay. So along comes Planck. So Planck offered an explanation for this. He suggested that maybe light is not a wave. Maybe light is a particle. this might seem a bit strange because we have done experiments where light is a wave. You remember the slit? Yeah, the double slit. The light goes through the double slit and spreads out. Only waves spread out. We'll deal with that problem next time. But just for today, Planck suggests that maybe light is not a wave. In fact, maybe light is a type of particle, like a proton, a neutron, an electron. It's some kind of particle. This is his suggestion. Okay, so we'll just make a note of that. Not only light, but other electromagnetic radiation, such as infrared, ultraviolet, X-ray, etc.
They're not waves.
Yes, that they are in fact particles of some kind. And by the way, I'm putting this in quotation, some kind of particle. Yeah.
He suggested a theory, but is that true?
Well, is his theory true?
Yeah.
Yes, it is. So, this is the problem we'll deal with in the next class. Planck's theory is that light is some kind of particle, and this particle, we are calling it a photon. So instead of picturing a wave as light, we can picture lots of photons, these particles coming out of the light bulb. But not just the light bulb, our mobile phone, our Wi-Fi, our internet, the X-ray machine at the airport, these are all photons, particles, not actual waves. Okay. Also, he worked out a formula for the energy one photon would have. So not only is he suggesting this idea of photon particles, he also has a formula for how much energy one photon would have. So the energy a photon would have would equal Planck's constant, no surprise, it is his theory, multiply the frequency of the wave. Well, what we thought was a wave, and what we thought was a frequency.
Can we change frequency?
I want to see what it is.
No, this is a new formula.
No, can't we change frequency into C over lambda?
Yeah, you could change the F into a lambda, so this could be HC over lambda if you want. Yeah, it's all, by the way, it's still also true.
It's weird, he said that it's not a wave, but he has a wavelength.
Yep. Things are going to start getting weird now. V equals C lambda. Sorry, I have that the wrong way around, sorry. C equals F times lambda.
Is that it?
Speed of light, please. I'm just saying, Carl's asked me, could you rewrite this formula with lambda in it? And I'm saying you can, because you can just use this.
But what does K represent?
Yeah, well, it's just a constant, like the big G in gravity, or the C in Einstein's theory. And I'll give you the value of the constant now. Yes? Question? No? Okay.
So, particles like protons and
Yeah.
electrons, they have frequencies or so.
Yes, and again, this is all things we'll get to in the next class. What is the value of H? H is Planck's constant, and it's on your calculator. I think I have it here as well. It's 6.6 times 10 to the minus 34. And what would the unit be?
Joules over Hertz.
Joules per Hertz, yeah. But what's Hertz? 1 over seconds.
So Joules seconds.
So Joule seconds would be the unit as well. Joule seconds.
Does the electronegative method is due to resonance?
No, not quite this actually. Just because the electrons get enough energy from the light and they're free. But the energy could be any form, I suppose. You could heat up the metal. It doesn't have to be light. It's just that light can be used to free it as well at the right frequency. Whereas if you heat it, I suppose you just have to heat it hot enough, long enough. Yeah, but you don't use a metal that melts before the electrons are freed. No. Yes, anything else? Okay. So let me give you a small problem to try using this formula now. A 100 watt bulb has light of wavelength 600 nanometers being emitted, something like this. Assume the light bulb is 10% efficient. So the question is, how many photons are released per second from the light bulb? So first you'll have to get the frequency of the light and use Planck's formula. I don't think this is too difficult. I'll show you the answer in a minute, but I think you can try it yourself first. This is a section A question. I've seen this in the exam almost like this, except they often like to do it with mobile phones instead of light bulbs, but it's the exact same idea. So they'll say a 4-watt mobile phone of 90% efficiency emits a wave of wavelength, whatever, nanometers. How many photons are coming from the mobile phone per second? Huh?
Number of photons.
Number of photons, yeah.
Power is energy times of work.
Power is work over time, yeah.
So energy over time.
Yeah, energy over time, correct, yeah. And the time is 1 second, so the energy equals the work, the power. Yeah. Who has an answer for me? Nearly? Okay. We do. We do. I promise you.
Minus 34? Yeah. The energy is really, really small.
Oh yeah, the energy is small. Yes.
It's 10 minus 1.
For the energy?
Yeah.
It could be a number like this, yes. But I want the number of photons. Does anyone have an answer for me? Not yet? Okay.
Is the number is very, very big.
Oh yes, the number of photons will be huge.
5 times 10 to the 13.
Not this. Will we do it? So here, you have power equals work over time. So what's the time here? 1 second. So you get power equals work. What's the power here? 10 watts, because only 10% is used for the light. So 10 watts is the power. So that means the work or the energy equals 10 joules per second. So therefore per second 10 joules per second of light is emitted. But Planck said that the energy equals his constant by the frequency. But remember, I said that's for one photon. That's the energy of a photon. So you have lots and lots of photons all the same. I just need to stick an N in here.
Can you repeat the final thing?
Yes. The energy is H multiplied F. This is Planck's formula for the energy of a photon, of a single photon. Just like the energy of a particle, kinetic energy is a half mv squared. These are all for single particles. So if you have many of them which are all the same, I just multiply this by n. So the energy is nhf. So therefore, 10 equals nhf. Do we know the F? No, we don't. We don't. But we know that C equals F lambda.
So we can find X.
Yeah, so we can say that 10 equals NHC over lambda. Therefore, N equals 10 lambda, hold on, 10 lambda divided by HC. Now type that in on your calculator and tell me what you get.
Nano is 10 to minus 9.
Nano is 10 to the minus 9. What you get?
Three times 10 to 19.
Yeah, 3.03, isn't it?
3.23 times 10 to the power 19.
19? Not 18?
19.
Okay. 10 to the power 19. That's a lot of photons per second coming out of the light bulb. Huge amount. That's it.
More than big computers.
Much more. What did you say?
More or less people on Earth.
Yes, much more. The people on Earth would be in the billions, which a 10 to the 9 number.
And more than most of people that ever believed in life.
Yep, definitely that too. Okay, so we're going to go back to the photoelectric effect for the moment. So if we think about the experiment I did, or not the experiment, but rather the idea that the light comes in, hits the metal, and then an electron is freed. What's the energy before the light hits the metal surface? No?
Energy of what?
Oh,
Energy of what?
Yeah, like if I'm trying to do conservation of energy, I want you to tell me what is the before energy and what is the after energy.
Of which object?
The system.
Oh,
Yeah.
positive.
Energy of photons.
Yeah, the energy of the photons coming in. Oh, by the way, you can assume that what happens is the light comes in, hits the metal surface, and then bounces off. What would happen to the frequency of this light after it hits the metal surface? Would it go up, go down, or stay the same?
Go down.
Yeah, why?
Because it loses energy.
It loses energy. Where does this energy go? To the electrons, to free them. So the energy at the beginning is in the form of the photons. They hit the metal surface and then they leave. And what's the form of the energy at the end? The new light and what else?
Electrons.
The electrons what? What energy will it have?
They're moving up.
Not quite this, much simpler than that actually. What energy?
Right.
Kinetic energy. The electrons move it, isn't it? Yeah. So the energy at the beginning is the energy of the photon. The energy at the end is the energy of the new photon frequency plus kinetic energy. There is one energy I left out from this though at the start. Not heat. There's no heat here. Forget about that. Huh? No. Kinetic of what? You can assume the electron.
The energy that the electron has in the beginning.
Yeah, what form is this? No. So you know in chemistry there are bonds to break. Ionization energy, yeah, there's bonds to break. In other words, the electron that's on the metal surface, it has a bond energy, a potential energy, an energy which you need to give it so you can free it. This you call in chemistry ionization energy.
So does it have it or does it need it?
It has it. And then when you free the electron, it no longer has it. So it's not quite ionization energy, but it's a similar idea. I suppose you can think about it like...
So it has energy but it needs more? Energy is like how much more energy it needs?
Yeah, well that's why I said it's like ionization, but it's not quite ionization. It's a type of potential energy. It's a bit like, do you remember in the last class we did the binding energy? When you have a proton and a neutron stuck together, you work out the energy of this bond. And therefore, that is how much energy the neutron needed to have so that when it hits it, it splits it. You remember doing this in the last class?
Yeah.
What I'm saying is the electron that's on the metal, it's just like that. It has a binding energy. This number, if you give it that much energy, you will free it. Okay? So it's just like the binding energy in the last class. It's a similar idea. So, to summarize, at the beginning, there are two forms of energy. The energy of the photon coming in, and the binding energy of the electron. Afterwards, the electron is free. It has no binding energy, it has kinetic energy. And there's a light that's coming off the metal, as you said, of a smaller frequency. So we can use conservation of energy here to get a formula. So the energy of the light at the beginning is HF1, I'll call it frequency 1, plus Now, the symbol here, I'll draw it. It's a Greek letter. It's called phi. It looks like this. This is the symbol for the binding energy. But we don't call it binding energy. I don't know why. Does anyone know the name of it? It's not called binding energy in this experiment. Not internal energy, good guess though? Oh, yeah, I don't think you'll guess this because it has nothing to do with the word binding, molecule, strong or internal. You'll never guess it. I just wondered if you knew it. It's called the work function. Yeah, I know, I don't know. It's such a ridiculous name because it has nothing to do with work, really. Well, not nothing to do. A better name would have been binding energy. Or even just, what do you call it? Not quite molecular, but some kind of internal energy. But anyway, it's called work function and the symbol is phi. This should equal the kinetic energy of the electron plus what? Plus the new frequency, so we'll call that F2. So it's H multiply F1 plus the work function.
But in the question, you did give the amount of photons.
No, and these questions typically, you're just looking at one photon hitting one electron in the exam. It's never anything like hundreds of photons are hitting the metal surface. It's always going to be, the question will say something like, a photon hits an electron, and here are the information, what is it blank? Now, this is the general formula, but there are some rather special cases. The first special case is when the light hits the metal surface and no light is reflected. So what has happened in this situation? All of the energy from the light was required to free the electron, and there was no energy left to send out a new light of a smaller frequency. So in this case, I'll call it case 1, no light is reflected. Basically all the energy was required to free the electron. Then the formula gets a lot simpler. It's just HF1 plus the work function equals kinetic energy.
Said, like in the beginning, that we can use only the surface of the metal, right?
Yeah.
Is it possible to use something that's not metal?
I don't think so. It's always metal, usually something like zinc. Is it possible? It might be possible, but it might just mean that the frequency required is so high it'd be difficult to produce. I just think a metal is the easiest one, that's all.
But it's possible to like plastic or anything.
It is possible, just maybe not practical. But it's possible.
The bond in the metal compared to the plastic, which one?
Well, no, the reason is the electrons are more free in the metal, so they require less energy to free them. Because, you know, a metal is a conductor, so it's like a sea of electrons. So in other words, the electrons don't need that much energy to be freed from a metal. Technically, though, I suppose you could do it with a plastic, but I'd imagine the frequency would be so high, it would be impractical.
But possibly you can use this frequency.
Possible. It's possible. It just might be expensive. Okay. think actually I might have I may need to have a sign here. Yes. I'm going to just, if you can make this here a minus, it's a negative number. And the reason for this is something which we have talked a little bit about in semester 1, and you might have talked about, have you done energy levels of electrons in chemistry?
Yes.
Yeah, and you know that all these energies are negative numbers.
No, only for exercise.
No, the electron energy levels are negative numbers. You know, have you done this in chemistry? You have the energy levels, and it says how much energy is at each level.
Oh, no.
You haven't done this?
No, not yet.
No.
The only energy we did was the Anderson again.
Okay, you haven't done, what are you doing in chemistry right now?
Oh yeah, all the ionization energies are negative.
Yes, this is what I'm talking about. All the ionization energies are negative. So, in physics and chemistry, when we want to show mathematically that it's an energy used to trap or bind, we consider it as a negative number. And we talked a bit about this, if you remember, in semester 1 with the mechanics, with the potential energy for gravity. Do you remember this? So I said, when something is in orbit, because it's trapped, we say it has negative potential energy. If it's free, what's the potential energy? 0. And if it's moving with some velocity, then its energy, it's not 0 then.
So it's possible for a method to completely resolve that.
That's the first thing, yeah? And the second thing is just make sure that is as a minus there, okay? And Lorraine does use minus, you said, for ionization energy. Yes, okay. So it's just like I said, work function is like ionization. Not the same thing, but it's like it.
I think if it's negative, then it's actually potential. I can't see any difference between ionization and...
I think the difference is with ionization there can be... No, actually, I suppose it's more similar than I thought.
Because basically, apart from ionization energy is the energy required, but the same way it's the amount of energy that bonds electrons with the nucleus.
Okay, I guess it's much more,
Yeah, it's the same, almost.
It's the same, except we have a different word for it, yeah. I suppose the difference is the electrons don't need to be around a proton or a neutron, they can just be free already inside the metal, whereas ionization is the energy freed from a nucleus. I guess we need a different word to distinguish this. Okay, anyways, case 1 is no light is reflected, so you get this formula. Which is in the formula book usually written in this form: HF1 equals kinetic energy plus the work function. So this is one version of the formula. This is the original version. You might call this like the full version.
This is the formula.
This one is not actually, I don't think.
No.
I possibly think this one might be, this case 1 here. Strangely, not the full one. This is something that will be given, or you have to work it out from the other information in the question. There is no formula for it. Okay, case 2 is the electron is just freed, i.e. not moving. So what I mean by this is the electron just about gets enough energy to be freed, but it's not really moving, it's just freed. And no light is reflected. So in this case we have HF1 minus the work function equals 0 plus 0. No kinetic energy, no reflected light energy. Therefore, HF1 equals work function. Therefore, F1 equals work function over H. If you think about it, this is the threshold frequency, because remember I said the threshold frequency is the frequency that just about frees the electron. So no energy was wasted here by giving the electron kinetic energy, it just gave it enough to free it. And no energy was wasted by having light reflected off of it. So, in fact, if you know what the work function is, you can know what the minimum frequency is to free an electron. And vice versa. If you know what the threshold frequency is, then you can know what the work function is. Question here?
I just wanted to ask if you can do that in any case that work function is equals to Planck's constant.
Yes, what you're doing here is this now is a formula for the threshold frequency for any problem. Case 2 is actually the threshold case, the case when just about free an electron with no reflected light. So as I was saying, yes, you can use this formula whenever you want, whenever you need to calculate the work function or the threshold frequency. This is it. So you have case 1, the full side. Case 0, the full case. Light comes in, frees an electron, gives it kinetic energy, and light is reflected. This is very rare in the exam. The next case, case 1, is more common. Much more common. In fact, 99% of questions are this. The light comes in, frees the electron, and no light comes out. It's fully absorbed. And the last case is really just to give us a formula for the threshold frequency. The threshold frequency is the work function over H. Alright, now you have a formula, so to speak, Joshua, a type of formula for the work function. It is the threshold frequency multiplied H. The only problem is you have to do an experiment to work out what the threshold frequency is. So in the question they'll give you one or the other. No, A. These are all A questions. Or part of a B question. So I'll give you one to try. So this... I want a... Okay, so here's my question. Light of wavelength 900 nanometers hits a metal surface. The work function of the metal is 1 electron volt. So you need to look up how many joules this is. I think it's also on your calculator. Here. Where'd you get this? If you don't remember how many joules an electron volt is, I'll tell you. It's constant number 23 on the calculator, 23. It is 1.6 times 10 to the minus 19 joules. Joules. Yeah, it's the same number. So it's the same button on the calculator, but it's also the charge in coulombs of an electron.
The work function is given as 1 eV.
Yes.
Does that mean I have to make it minus 1 eV or just 1 eV?
The work function will be 1 eV, but in the formula make sure you put the minus in front of it. So technically the work function is a positive number, but it enters the formula as a negative. So my question is, what is the maximum velocity, maximum speed of the freed electrons? So you need to think about this very carefully. You need to assume the conditions that make the electron as fast as possible. So do you think, in this case, light will be reflected or not?
Yes.
No.
Because
No, you don't want any light reflected. You want all of the energy of the light to go into the electron to give it maximum kinetic energy and therefore maximum speed. I want to know what is the maximum possible speed of the electron. So we need to assume all the energy has gone into the electron. I'm not saying this is the speed. I'm not saying this is the speed. I'm just saying it is the maximum the speed can be.
does that mean it's like case 2?
Case 1.
Case 1.
We're supposed to use the mass of an electron.
Yeah, you need the mass of an electron as well in the formula, which is, I don't know, it's on the calculator too. I gave it to you right there, it's 1 electron volt. Some people have an answer?
It's less than 1.6.
I'm just gonna, you've got a calculator.
Okay, is that equation you right?
I don't know. No.
So do we use the value of the work function as a negative one, or do we put it in the formula as positive, but because of the minus?
Tommy's just asked me that. Tables have turned. The work function is quoted as a positive number, but it goes into the formula as a negative number. So in my formula, I put a minus in front of it.
Oh, okay.
Yeah. But if I said what is the work function, you don't say the work function is minus 1 eV. You say the work function is 1 eV, but it goes into the formula as a minus because it's a binding energy. Right, who has an answer? Do you have an answer? What is it?
it's the same sentence, I think.
Same, yeah. So, here's the answer. Maximum speed means maximum kinetic energy. That means all of the energy gets turned into kinetic energy. That means the HF1 plus minus work function, that equals kinetic energy plus 0. We say that there is no light afterwards, that all of the energy goes into making it have more kinetic energy. So that means a half mv squared equals hf minus work function. So that means a half, well, I'll just multiply across, v squared equals hf minus work function multiplied by 2 and divided by the mass of an electron. So then that means the velocity, which is the maximum possible velocity, is the square root of 2 times, well, square root of all of that. What's it about 3 times 10 to the 5, is it?
Yeah, 3.6. Yeah. 3.6
Okay. So round about, if I write that in, it is, but you know, it's 1,000 times smaller than the speed of light, so it's big, but not astronomically big. Okay, this is a very typical common section A question. It is number 1 on your calculator, number 2 on the formula book, number 3, leave me alone, okay?
All the constants are in formula.
Yes. They will not expect you to remember any constants. They know who they're dealing with, okay? So you don't need to remember any numbers. No. Yes, even Mr. Stephen doesn't. Yes. Okay, now, interesting, we have seen that when light hits a metal surface, it will free an electron. When an electron hits a metal surface, it could release some light. The reverse is true. And all the formulas are exactly the same, you're just looking at the picture backwards. So now the after picture is the before picture, and the before picture is the after one. It's completely reversible. So your light comes in, releases an electron. If you take the electron, turn it around and send it back with the same speed, when it hits the metal, it will release the light with the same frequency at the beginning. It's completely reversible. Yes. Yeah. It's the process in reverse. This is good because it means we have a way of creating light. If you hit an electron at a metal surface, you can release light. But not only that, if you change the speed of the electron, what will happen to the frequency of the light? It'll change as well, won't it? So if I want a high frequency light, what do I need my electron to be doing? Move at a high speed. Okay. How can we give an electron a speed? How can we get an electron moving? What could we do to it? No, come on. Magnet's one way, something a little simpler. No. That's so prehistoric. Give me something modern. Something precise. Heating is not precise. Great battle now. Now you need some way of giving the electron a precise speed. What about if you put your electron in an electric field? Alright, fine. You put your electron in an electric field. What's the formula for force on an electron in an electric field? QE. And what's the Q? Charge an electron. And what's the formula for the E, electric field strength? Voltage over distance. Can you control the distance? Yes. And can you control the voltage? Yes. So you can give an electron whatever speed you want.
You said the proper QE.
No, I didn't. What's QE representing? The force. What's the formula for force from Newton's second law? Ma. So the acceleration will change the speed. You can put the electron at rest and then give it whatever speed you want by giving it whatever force you want for as long as you want. Oh no, Hannah, what's your question? Go for it.
It's just a question.
Go on, yeah.
In the formula, do I have to use 1 as a work function or 1e as a work function?
The work function is 1 electron volt, which must be converted into joules.
Or if you want just a kinetic energy, you can integrate.
If you leave it at EV, then your kinetic energy will be in electron volts.
Use 1 or 1 EV?
Neither. Use 1 EV in joules, which is like 1.6 times 10 to the minus whatever. Does that answer your question or not?
Yeah.
Okay. What am I saying? Right, anyway, do you remember recently we had a simple formula for working out how much energy an electron has in an electric field? Do you remember doing this? So yes, F equals QE, but we don't want to deal with force. It'd be much nicer if we just deal with energy, because then we can say the energy in the electric field equals the kinetic energy when it leaves the electric field. This kinetic energy then gets changed into light energy, and we can work out the frequency. Does anyone remember the energy of an electron or whatever in an electric field? No? Yep. If it helps, I did it in B401. Does that help?
Can you repeat the question?
I'll tell you it's the energy of a charge in an electric field. No, look at me, you forgot it, so I'll say it again. Look at me. The energy of a charge in an electric field is equal to E, the electron charge constant, multiplied by N, the charge number, plus 1 for proton, minus 1 for electron, multiply V, the voltage of the electric field. So the energy provided by the electric field equals E and B. You remember I wrote it on the board in B401, but there was only 4 of you there. Oh, that's why. There was only 4 of you there, wasn't it? I think it was you, the 2 of you, and
Daniel.
You came in late to that when Frappuccino began.
No.
No, that wasn't that day. Daniel, yes, it was the 4 of you. And the other 4, we missed it. And because it was in B401, it wasn't recorded, so it sucks to be you now. Right, so I'll remind you what the formula is. Energy in electric field equals E and B, where E is the charge of an electron or proton, same number. N is the charge number, i.e. plus 1 for proton, minus 1 for electron. It's the number you use in chemistry. And V is the voltage.
Can we use it in the example of the uranium?
Yes, and it's not in the formula book. So another reason why it sucks to be you right now, because you missed that formula not in the formula book.
So we don't need to do this, we can just use it straight away.
Oh yes, yes, yes. You can just go straight in with E and V.
Is it a common question where we need to use it, apart from the one that we saw?
I would say 20, 25, about 1 in 4 chance of getting a question that requires this formula in the exam.
Well, if we wanted to use like F equals to E,
Yeah.
and see how we do that.
But then you see, this is the reason we prefer this formula, because if you use F equals QE, then you have to start talking about UVATS and F equals MA, so you can work out the V. But if I use this formula, I can just say the electric field energy, the energy provided by the electric field will equal the kinetic energy when it leaves the electric field. Okay? You get it? So it makes the calculation a lot easier and a lot quicker.
The electric field.
Right now we are in a gravitational field. This is in a gravitational field. Yes? So what type of energy does it have? Gravitational. What's the formula? mgh. And if I let go, what will happen to it? It'll fall and the energy will be converted into kinetic. Right. This is a metal plate, that's a metal plate, this is an electron. If I let this go, it will move to the positive plate. So the energy it has in the electric field gets converted into kinetic energy. It's directly comparable to gravitational field. The only difference is gravitational field, the mass is only positive. Whereas in an electric field you can have positive and negative, so it can move up as well as down. But of course, if you have negative mass, it could move up. Find out next week. We'll have negative mass next week. Right, so, let me give you one to try. Listen carefully. I'm just going to read the question, but I'll type it in a minute. So, this is what's happening. I have an electron that enters an electric field. It will accelerate and then leave the field. Then it leaves the field and hits the metal surface. When it hits the metal surface, assume it all gets converted into light. So light comes off here. So my question is, if the voltage is really, really high, so here I have a voltage of 50 kilovolts, so the voltage is 50 kilovolts. I would like to know what is the frequency of the light at the end for one electron that enters. So in other words, one electron can make a photon with what frequency? So one electron will convert into one photon. What's the frequency of this photon?
Oh, okay.
You get that? So you actually have all the information you need to do the calculation. No, actually, do I need to give you a work function? No, I don't actually need to give you, or do I need to give you a work function? No, I don't need to give you a work function.
There's still the effect formula for case 1, like case 1 formula, right? But, yeah, right? And our kinetic energy would be this one.
No, I don't need the work function. Because what you can say is the electric field energy gets converted into kinetic energy. This kinetic energy can get free the electron and blah blah blah. But you can skip over that step because you know that the energy is constant. The only energy at the end is what? The energy of the photon. So the energy of this photon should equal the energy of the electron as it was just about to hit the metal plate.
And the frequency
Okay.
which will equal the kinetic energy when it just about leaves the electric field. So you can actually skip from your calculations the work function. It's not a necessary thing to calculate.
Right, then yes.
Essentially, yes. Yes.
So, can the frequency be negative?
Oh, no, man, no.
N minus 1.
Yeah, but I mean, I should really, the n uses 1. You only put in the plus, Joshua, you only put in the plus or minus if it's free or not free. So when the electron is in the gravitational field, the energy, potential energy is positive because it's accelerating. If it was trapped in the electric field, it like going around, would be negative energy, and if it was free, it'd be 0. So I know, use 1.
3.36.
I think this is very
Very low frequency.
Very low frequency? I don't think so.
I think this is why we just leave the work function.
I'll show you that in a minute. Who has an answer for the frequency? Say again? Correct. Next question is give me the wavelength. The frequency? 10 to the 19, 1.3 times 10 to the 19. So next I want the wavelength. What is nano? 10 to the minus. So is this bigger or smaller than nano? Smaller. 600 nanometers is roughly the light you can see. It's visible light. This is many times smaller than visible light. So what type of electromagnetic wave is it? It's very, very small wavelength. Very big frequency. No, you're looking at the wrong side. Too small. Step it back a bit. X-ray. So congratulations, you've made an X-ray machine.
Yeah.
This is an X-ray machine. This is exactly how an X-ray machine works. They have a 50,000 volt electric field. They fire electrons. No, they don't even fire electrons. They heat up an element and put this in the electric field. The electrons are released, enter the electric field, fire out, hit a metal surface, X-rays come off. So you take your metal surface and you put it at an angle at the person you want, and there's an X-ray machine. Yeah. So like here, yeah. I'll do it in a second, yeah. So here is a heating element. It heats up, so the electrons are released, and then here is an electric field. It goes in, you need a little hole at the end though, so when the electrons go through, they escape. You put a sink at 45 degrees, so the electron comes in, hits it, and the light that's released goes off this way. Okay? And then you will all get a nice X-ray. Then we put a big picture on the back wall, and then all your X-ray will appear on the picture. The special material, I can't remember what it's made of, but it will. Yeah, it's a material which will turn white when X-rays hit it.
What is the
I don't know actually.
Same case, like during the year, that time school people were working on like trade sheets.
Oh really?
Yeah.
Alright, I'll have to look it up.
My grandmother had collants with some classical collants X-ray.
That is cool. That is cool. So you can use vinyl to do this then?
I guess, yeah.
I'll definitely look that up now. So you have vinyl records as X-ray screens at home?
Yeah.
Nice, nice. Okay. So I'm going to have a look at this one. I'll do it on the board, okay? But this is just an X-ray machine. Now, the only problem with the X-ray machine is that the metal will get really, really, really hot. So you need some kind of really good insulator, like tungsten or something like this. You done this in chemistry? It's what they use for in chemistry labs, I think, when you're holding something really hot. So anyway, in other words, you just make sure your metal plate has some material on the back of it that can really absorb heat, because otherwise it won't last that long. I think it's only used in labs, but you might have some kitchen material at home that has some of it in it, like for pots, you know, for the handles. Yeah. Let's look at the calculation here. Yes.
What's the velocity of the particle in that an electric field?
What do you mean?
Their formula.
No, but I'm going to do this now anyways, okay? So the energy in the electric field, that should equal the energy as it leaves the electric field. So that equals the kinetic energy as it exits the field. Okay? That energy is kinetic. Now what will happen is this will hit the metal plate. So the energy then will be hf plus the work function. Wouldn't it? Sorry, I'm getting a bit confused here.
Its formula is still the same. Kinetic energy is hf minus.
Yeah, sorry, let's go back to the formula. What is it? It's this one here. Yeah. So this is the formula for kinetic energy. So that equals that. Yeah. So that equals hf minus work function. Okay. So the work function here, you do need to know it, but you don't need to consider it in the formula. And the reason for this is because in this example here, the work function is so much smaller than hf.
Why? How do you know that?
Well, typical okay. Somebody tell me here how many joules they got for what is hf? Can you just tell me how many joules that is? So type in h multiplied the frequency. Ten to the minus 15. And what is 1 electron volt? 10 to the minus 19. So in this example, and only in this example, the hf is 1,000 times bigger than typical work function values. Work function values are usually of the scale 1 to electron volts. Because the hf is 1,000 times bigger, it can be ignored. This is not always true. It's only true for this one because the energy is so big.
How do we know them before we start solving it? Because we know the F when you finish something.
You're supposed to know because your teacher should have said work function values are typically 1 electron volt. They're a little more, a little less. I forgot to tell you this. That's why. So I'll write it here. So, what we can do is, we can say this energy here, it's all equal. So this energy at the start equals this energy at the end, which is what you said here, right? ENV equals HF. So, therefore, ENV equals HF.
Yeah. So why is the kinetic energy being, why is that replaced with the other?
What? What are you asking me?
According to the formula, is HF plus work function equals to kinetic energy.
Yeah.
Yeah. So you ignore the work function.
Yeah.
And so you make HF supposed to be equivalent to kinetic energy.
Yes. And kinetic energy equals the energy in the electric field. Because Tanish, look, these are all equals here.
Yeah.
This equals this, equals this, equals this, equals this. So I can say this one here equals the last one here. Therefore, I get this result. Because the energy in an electric field is EMV. You know, if I said kinetic energy becomes something, okay. Electric energy becomes kinetic energy, becomes something else, blah, 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 becomes light at the end. I can just say the light at the end equals the electric field energy at the start. Now, of course, you can still calculate the kinetic energy as well, but we want to do that. What is the end here? What statement I made? All these statements are correct. The energy in the electric field equals the energy as it leaves the electric field, which is kinetic energy as it exits the field. Kinetic energy becomes HF minus work function from the formula we did today. However, work function is so small compared to HF and kinetic energy, it does not add much, so we can ignore it. In this example only, therefore, the electric field energy at the start will equal just HF at the end.
Do we mention this
Oh no, you wouldn't get this in the exam because they don't like giving questions to students that require them to assume things. So, if you got this in the exam, they would say, you may consider the work function equal to 0. They would definitely tell you that in the exam. Because you've no way of knowing that you can do that here. I'm telling you you can, I won't tell you in the exam. Okay? Anyways, what is the n here? It's 1. So we get, but n equals 1, so then EV equals HF. And so F equals EV over H. So what did you say the F was? When you put in EV, this is 50,000. What is it?
1.21 times
10 to the positive 19 hertz. So what does the wavelength equal? That's C over F. Whatever, 1.21, yes. 2.48 times 10 to the power of minus 11 meters, which equals, nano is minus 9. Unzip that pencil case.
to a point for the 8 times 10 to minus 2 nanometers.
Hang on, it's 0.0248 nanometers. This is an X-ray. There you go. Your first X-ray machine. Congratulations. Seriously, if you think about it, it's really, really simple. What things would you need to find at home to make this?
Electron.
Electron, yeah. First, you need some kind of heating element. Where did you get a heating element? For your kettle. Good. Then what do you need next? You need 2 metal plates. 2 metal plates. Wherever you get metal plates from. Okay. Now, how do you make the electric field? You need to put a battery around it. What voltage do you need?
A very high one.
Yeah, 50,000. But you know how to change the voltage. What's the device that changes the voltage? Step-up transformer. What's a step-up transformer? A piece of iron with the wires wrapped around it. Can you get this? Of course. Then what do you need here? Then you need a little hole in the metal and a sheet of metal. Zinc. So there you go. That's what you can do over the summer. You can build an X-ray machine. And actually, as Tom just said, you know those old records for music, the black records, they're like this big. When X-rays hit that, you can see the image on these.
Probably.
Probably, he thinks so. So if you find some old if you find some new records, if you just put that beside the plate, then when the X-rays hit this, the image will appear on it.
So, the heating element would be metal plate and electron bar voltage.
The heating element will release the electrons. They go into the electric field, they're accelerated, they hit the metal plate, and then the X-ray hits the record, the music record. So I'm just saying, if you think about it, it's a very simple machine. It just, might kill you. So just be careful, okay? Don't stand in front of it turned on too long. What's the recommended number of X-rays per year, the maximum?
1, 2.
No, I think if you really need to, 10 is the limit.
What if it goes
That much in left.
Yeah. Well, it's not so bad because usually people get X-rays, like you might get a dental X-ray and then you might get a chest X-ray, so it's not as bad as if you get the same spot X-ray all the time. Okay. 10 is the maximum. Over that and, yeah, no good. Alright, here, some questions as you go.
When are we doing the spiritual
Not now. See, the extra maths class tomorrow. The extra maths class tomorrow. Dude, that's cool. Yeah, see you tomorrow. If it's classes are cancelled, you can do it in the tutorial on Monday. Okay. Monday. Okay. Monday now. Keep them. If you see Mohammed Abdel Wahab, give them to him.
What? I put in my garden.
See you.
Bye.
See you.
That's up here.
Yeah, the problem is now I've been getting busy with stuff in class. I don't have time to do it now. So The thing is as well, Tanish, is when we finish the course I'm just going to do revision, so it's going to be questions. But is it from the book or a past exam?
That's from the book.
What topic?
Integration by declaration function.
Alright. I'll do this next week in a math class. Yeah.